Okay, class, in this video we're going to find the equation of lines in vector, well, in all kinds of forms. So mainly in vector form, but also parametric. So what do we do? So first off, we're going to say we have a vector that goes to a point on my line. I'm going to pick A here, and I'm going to call that vector P. And then I have a vector that goes from A to B, and I'm going to call that vector D. All right? And so if I want to go from the origin to B, basically I would just add those two vectors together. So we're going to say, for lack of a better thing to call it, I'm going to say that we have the vector equation of a line RT, and this is going to equal P plus a scalar multiple of D. Okay, so if I needed to get to this point, I would just multiply by D by some number that would lengthen that vector out, and then P plus that vector would get me to that other point. So D, I like to refer to it as a direction vector, so I might call it that fairly often. But IB calls it the velocity vector. So you should be aware of that. Okay, so let's do just a couple examples of this, and I guess I've got one more thing to sort of show you that's a little different form. So we're going to find the equation, and we're going to do a 2D example first. So the equation of the line containing 2 points. So let's see, what do we want our points to be? I picked A, which is 2, 3, and B, which is 4, negative 2. Alright, so this process is extremely straightforward. Okay, so D is going to be the vector that goes from A to B. And so in the old-fashioned form, that would be you just subtract terms. So 4 minus 2 would be the x components, and negative 2 minus 3 would be the y components. And I'm going to write this as a column vector, so this would be the vector 2, negative 5. Okay? A is merely just the vector that goes from the origin to, or P, sorry, is merely the vector that goes from the origin to A. So it's just a vectorized version of A. So that's going to be 2, 3. Okay? So R of T, and in IB they frequently write it like this, so XY. Okay, so that's going to equal that position vector P plus T times 2, negative 5. Okay? IB also likes to use weird things. Instead of T, they may use a lambda or some mu or some silly thing like that. I guess I should say that in 3D we just have a third component. So 3D, third component. So you'd have an X, Y, and a Z, and you would sort of do the same thing. So I've got one more example, and then I've got another last little thing to talk to you about. So find the equation, the E equation, hard to write and talk at the same time, of the line parallel to, so it's going to be parallel to another line. Okay, and what's it going to be parallel to? So this is a 3D example, so XYZ equals 2, negative 1, 4 plus T times 1, 3 minus 5. And what else do we have to know? We have to know a point on the line. So through the point 5, 7, 9. Okay, so that's the question, and this is really straightforward. We know the point on the line, and we know the direction vector or the velocity vector. So what we're going to do, we're going to use it's parallel to this line, so we might as well just use the same. Any scalar multiple of this velocity vector would work. So we're just going to multiply times 1 because that's the easiest. So my answer here is going to be that XYZ equals 5, 7, 9, that's the point on my line, plus T times 1, 3 minus 5. Okay? And notice parallel, so same, here I'll do IB speed, same velocity vector. Okay. Furthermore, we can write these parametrically. So I could say that x equals 5 plus t, y equals 7 plus 3t, and z equals 9 minus 5t. Okay, and one last little thing, I just want to make sure you see this. So we can actually write that in rectangular form. Okay, it's kind of weird looking though. So how do I do that? So if I solve everything for t and then set them all equal to each other, what do I get? So I get, here I would get t as x minus 5, here I would get y minus 7 over 3, and there I would get 9 minus 5, or 9, z minus 9 over negative 5. Okay, so x minus 5 equals y minus 7 over 3, which equals z minus 9 over negative 5. And this is what we call this, these are what we call the symmetric equations. And so lastly, let me just sort of write down all three forms. Okay, so one form of a line would be x, y, z equals x0, y0, z0 plus t times a, b, c, which would be your velocity vector. Okay, so this would be the normal vector equation of a line. You can even combine it and make it one vector if you like. And then the parametric form would be x0 plus at for x, y equals y0 plus bt for y, and z equals z0 plus ct for z. And then the symmetric form, what would that look like? It would be x minus x0 over a equals y minus y0 over b equals z minus z0 over c. And that's about it. I do have some problems I'm going to put online for you to look at.